the normal distribution, and the empirical rule. Our objective, given a normal distribution, state the empirical rule. We have done a fair amount with the empirical rule up to this point. We're now going to apply it to the normal distribution. So a couple things we know. The normal distribution is a distribution of continuous data in which the data tend to cluster around a central value. That value is the mean, which is equal to the median and the mode, but we're going to focus on the mean. And so I've drawn a dashed line down here through the mean, and we'll label it with mu. Okay? In the normal distribution, we have symmetry about the mean. 50% on the right matches 50% on the left. There is symmetry as you go from one side of this line through the mean. And I just spoke to this one, 50% of data above and below. Let's also remind ourselves that the standard deviation is a measure of how spread out the data are. Okay? If the data are not very spread out, this will be a tall, skinny bell shape. If the data are quite spread out, this will be a short, kind of flat bell shape. Okay? Standard deviation is a measure of how spread out the data are. The empirical rule tells us, the empirical rule being 68, 95, 99.7, for a normal distribution, it tells us the following, that approximately 68% of the area under the normal curve is between the mean plus 1 standard deviation and the mean minus 1 standard deviation. So between here and here lie approximately 68% of the data. Just over 2/3 of the data will fall in this close-in range next to the median. And that makes sense, right? If things are normal, for example, our heights, most of us, are close to the mean. If the average height for an American adult male is 5'10", most of us are within 3 or 4 inches of 5'10". Most of us are close to the average height. Okay, 95% of the area under the normal curve is between the mean minus 2 standard deviations and the mean plus 2 standard deviations. Okay, here's 2 standard deviations minus. Here's plus. 95% of the data is right there, the area under that curve. And finally, almost everything. Everything, everybody, every tool that's made, every light bulb, you name it. 99.7% of the area under the normal curve is between the mean minus 3 standard deviations here and the mean plus 3 standard deviations here. Now remember, this curve gets closer and closer and closer to this horizontal line, but never touches. But really, when we're talking about 99.7%, there's not a whole lot that's out there in Never Never Land. Okay, we're really got everybody in here with very, very few exceptions. Okay, let me shift papers. And I've put together, I think we've seen this before perhaps, but I did a copy and paste from somewhere on the internet. And I came up with this breakdown that shows it all very clearly. Here's the mean plus 1 standard deviation, plus 2, plus 3, minus 1, minus 2, minus 3. Here's, if this is 68% and the graph is symmetrical, then 34% is above the mean and 34% is below the mean. The same thing with 95%. Okay, this half is 47.5%. If you add those two numbers up, this half is 47.5%, etc. Notice above 3 standard deviations is only 0.15% of the data. We really don't get ourselves too excited about that 0.15%. And below 3 standard deviations is also about 0.15% of the data due to symmetry. And again, not a lot to get excited about. We really want to focus on the 99.7% if we're going to look at data and make comments on that or interpretations. Two things about the normal curve that we want to remember. It is the normal curve is modeled on the histogram. It's created as the class widths get smaller and smaller. The area under the curve, okay, remember it goes on forever, but it gets, obviously it gets narrower and narrower as you get out on these wings. The total area is 1 or 100%. But when we talk about proportion, the area is 1. It represents two things, the proportion and the probability. And you want to remember these two things when you interpret this. It represents the proportion of the population with the characteristic described by the interval of values, and it represents the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. Represents the proportion, represents the probability. Let's take a look at an example where we can put that to use. And you can see how that looks with some real data, some wording around it. Okay, let me get myself organized. I think I'm organized. The serum total cholesterol, I think that's serum? Yeah, the serum total cholesterol for males 20 to 29 years old is approximately normal. Okay, it's approximately normal. It's normally distributed with a mean of 180 milligrams per deciliter and a standard deviation of 36.2 milligrams per deciliter. So total cholesterol for men, go figure, it's normal. Most of us are close to this. And as you get further away, you'll have fewer and fewer of these 20 to 29-year-old males who will be further and further away from this number. Okay, draw the normal curve. Okay, let's go and draw us a line. And we'll just kind of draw a normal curve. We're not overly concerned about perfection. There you go, that's pretty good. All right. Normal curve, we have a mean. The mean is right here at the pinnacle, the peak. And the mean is 180. And it has a standard deviation of 36.2. So I'll go out here with one standard deviation. And this is going to be 216.2. How did I get that? I took 180 plus one standard deviation plus 36.2. And so that's where I am. And I'll go back one standard deviation, subtracting 36.2, and the answer is 143.8. And again, that is the mean minus 36.2. We could continue and do 2 standard deviations and 3 standard deviations. We're going to stop right there. Okay, we'll stop right there. An individual with total cholesterol greater than 200 milligrams per deciliter is considered to have high cholesterol. So if you are a male, 20 to 29 years old, and you are greater than 200 milligrams per deciliter of your serum total cholesterol, you have high cholesterol. Let's shade the region under the normal curve to the right of x equals 200. Well, here's x equals 180, the mean. Here's 216. So we'll call 200 ballpark about here. That's probably, let's think for a second. Let's move it a little bit to the right. I think it's probably closer to about the middle, right? There's somewhere right here. It's a little bit to the left of the middle, but we'll go to right here. So there's my 200 line. I'm going to put a dash in here, and it says to shade the region to the right. So I'm going to shade the region to the right, and again, it goes on forever. Okay, so anyone who has readings above 200, anyone who are in this shaded region, any of these males, 20 to 29, have high cholesterol. Okay? All right. Now, part C. Suppose the area under the normal curve to the right of 200. So suppose this area is 0.2903. Let's remind ourselves, the total area under the curve is 1. So this part is going to be less than 1. Well, that's a half. And what we're being told is this area is 0.2903. Provide two interpretations of this number, of this result. Okay, one interpretation. Remember our two interpretations. Proportion and 2. Let's make sure you can see that. Sorry about that. Proportions and probability. Those are our two interpretations. Okay? Proportion. The proportion of 20 to 29-year-old males that have high cholesterol they spell cholesterol, O-L-E-S-T-E-R-O-L, is 0.2903. Okay, so the area under the curve, which we're told is 0.2903, tells us the proportion of these males that have high cholesterol is 0.2903. It also tells us the probability, okay, proportion, probability. The probability, let me get my pencil let a bit more out here, P-R-O-B-A-B, the probability that a randomly selected 20 to 29-year-old male has high cholesterol is 0.2903. If you want to express that probability as a percent, 29.03%. So the probability that a randomly selected 20 to 29-year-old male will have high cholesterol is of just under 30%. So those are the two meanings of this number, which is the area under the curve. Okay, so there you have it. The normal distribution and applying the empirical rule.